So continuing on, we discussed the Claisen condensation and the Michael reaction last class session. And I just really want to emphasize how general the Michael addition and conjugate addition reactions of enolates are. So as long as you have an alpha beta unsaturated carbonyl compound and a highly activated, for example, diketone or beta ketoester or a malonate, you can see a reasonably efficient Michael reaction. So your Michael acceptors are your electrophiles. These are your alpha beta unsaturated ketones, aldehydes, esters, amides, nitriles, and even nitro groups, which can be thought of as enolate equivalents. While your Michael donors serve as your nucleophiles. These are your beta diketones, beta ketoesters, malonates, beta ketonitriles, and even just lone nitro compounds. Because the nitro compounds have highly acidic alpha protons, it's easier for you to generate an enolate. So I just want you to know, we've seen Michael reactions in beta ketoesters and diketones and enones, and I just want to really showcase that this reaction is quite general. Does this idea make sense to everyone? That as long as you have a reasonably stabilized, easy to form enolate, and as long as you have a reasonably electrophilic alpha beta unsaturated compound, you can see an appreciably efficient Michael reaction. Okay, so let's keep going then. And let's talk about another way to perform conjugate addition reactions, and that's by utilizing enamines as enolate equivalents. We've talked about previously how you can use enamines for alkylation reactions, and this is really based on this idea that the enamine is equivalent to an enolate in their reactivity and can be used to accomplish enolate-like reactions under milder conditions. As a refresher, enamines can be prepared from a ketone and a secondary amine, and enamines form to give the least substituted enamine, making an enamine a useful kinetic enolate equivalent. Carbonyl condensation reactions involving enamines are known as the Stork reaction. So for example, if we take cyclohexanone and we treat it with pyrrolidine, we can prepare the pyrrolidine enamine. This enamine functions as an enolate equivalent and can participate in conjugate addition reactions. The beauty of this reaction stems from the fact that once we have our conjugate addition product, just like when we had a beta ketoester, we can quench our formed enolate via a proton transfer. This reforms our enamine, and this enamine is stable in solution. Now you may ask, why don't we see a condensation onto our carbonyl? Well, let's answer that question. If we see condensation onto our carbonyl, we would form this already quite odd looking structure. So first, after condensation onto the carbonyl, which we don't see typically, we would form this aminium ion and we'd form this alkoxide species. Now this alkoxide ion is pretty hindered. So even if we're thinking about this just in terms of aldol-like reactivity, this congested center is not likely to form. Further, we can't eliminate water. So this 1,2 addition is reversible, and we can easily kick out our enamine as a leaving group to reform our enamine starting material. So just like running an aldol reaction on a congested substrate, or trying to form a very hindered stereocenter, addition of our enamine into our carbonyl is not favored. So this enamine can then be hydrolyzed under acidic conditions to unmask our desired diketone. So the benefit of the Stork reaction is it allows you to perform a conjugate addition reaction under mild conditions. It favors alkylation and reaction at the least substituted alpha position, and it allows us to isolate the diketone for use in later reactions. Does this idea of enamines as enolate equivalents make sense? Perfect. So let's keep going then. And let's show the full mechanism. So just as a refresher to show how this enamine is generated, if we take cyclopentanone and treat it with catalytic hydrochloric acid and pyrrolidine, and pyrrole, we're first going to protonate our carbonyl. From here, our nucleophilic amine will attack our carbonyl carbon, and we would form a tetrahedral intermediate. From here, we're going to see a series of proton transfers to free up a lone pair on our amine. And to activate our alcohol as a leaving group. From here now, we can kick out our leaving group, which is water, and generate our aminium ion. From here, this aminium ion can be readily converted into our enamine. Let me redraw that. Via deprotonation of our alpha position. So we've deprotonated our alpha position, and we've generated our enamine. From here, our enamine can react with the electrophilic beta carbon of our enone to generate our conjugate addition product. From here, we can protonate our enolate. And this protonation step and protons transfer step will likely occur in an intermolecular fashion rather than intra. That in turn gives us our enamine, which can be isolated and is a reasonably stable species. But in most cases, to unmask the desired diketone, we're going to treat with aqueous acidic conditions to hydrolyze our enamine. So under aqueous acidic conditions, we protonate our enamine to make our aminium ion. And then from there, the aminium ion can be attacked with nucleophiles such as water. We form a tetrahedral intermediate. And of course, just like before, if we're trying to hydrolyze this enamine, we are going to have to protonate our nitrogen atom and deprotonate our oxygen atom. From here, let me just redraw this part. I'm going to label this group as R just to avoid repetition. Okay, so now that we've activated our amine as a leaving group, we can now kick out our leaving group and reform our desired diketone. We're now one cleanup step away. All we have to do is deprotonate our carbonyl, and that in turn gives us our desired final product. So does this full mechanism for the Stork enamine reaction make sense to everyone? We've seen the mechanisms for enamine formation and enamine hydrolysis in previous chapters. Any other questions on this mechanism before we move on? If we don't have any other questions, let's move on. In this case, let's try to predict the product of the following reaction and draw a mechanism for steps 2 and 3. So you can draw just the product from step 1, and then I'd like you to show how the product from step 1 is used and the mechanism for steps 2 and 3. So let's work through this example and let's try to predict the product from each step of this reaction sequence and draw a mechanism for steps 2 and 3 of this reaction sequence. As we work through this example, I'd like students to share their responses in the chat, verbally, or annotated on the class whiteboard. And if you have any questions that I can address as we work through these examples, don't be shy to ask them in the chat or verbally. So do we have any questions, or does anyone have any initial thoughts of what's going to happen in each step of this reaction sequence? So in the first step, if we treat a ketone with a secondary amine and hydrochloric acid, we are going to form an enamine. Yep, exactly right. Interestingly enough, and this is really important to note, the enamine forms to give the least substituted enamine, as enamines are very sensitive to steric hindrance due to the effect of steric hindrance on the resonance stabilization of our enamine. We talked about this previously. So now that we have our enamine, which is an enolate equivalent, the enamine is nucleophilic. Sure. So now that we have our nucleophilic enamine, do we have an electrophile available to react with this enolate equivalent? is there an electrophile available that can react with this enolate equivalent? We do have an electrophile, right? We have this alpha beta unsaturated ester, and this alpha beta unsaturated ester is electrophilic at the beta position. So as the student noted, we can attack our beta position and generate our conjugate addition product. So would anyone like to show the next step for this mechanism? So now that we have our conjugate addition product, what happens next? So we have our conjugate addition product, and we have this aminium ion generated. How do we quench out this enolate? What happens to quench out this enolate? Is this the final species that we have floating around in solution, or does some other key step happen to convert this enolate generated into a more stable species? Yeah, the enolate can be protonated for sure. Exactly. So we can protonate our enolate. And most importantly, we can convert this iminium into an enamine once again. And it's this enamine that remains in solution. Okay, so it's this enamine that sticks around at the end of step 2. So if you treat this compound with hydrochloric acid, methanol, and water, what will we expect to see? Would anyone like to try and draw a mechanism for this last step to unmask our desired ketone functionality? Would anyone like to try and share the mechanism for enamine hydrolysis? Since we want to unmask the ketone to use it for further reactions, would anyone like to try to annotate that mechanism? Or would anyone like to try to share the next step in this reaction sequence? Yeah, we can protonate the enamine. Yep, that's the first step. So from here, we now make our aminium ion. So what happens next? We now have this activated electrophilic iminium ion. How do we hydrolyze this imine? This iminium carbon is electrophilic, so methoxide or even water can attack. If we want to hydrolyze, we're likely going to need water to attack. Is there supposed to be a methyl group? Yeah, we forgot the methyl group. Yeah. There we go. So we attack our iminium ion, and now we get a tetrahedral intermediate. Sure. So how do we push this reaction to favor loss of our amine? How do we push this reaction so that we can lose our amine? Would anyone like to draw the next step for this mechanism? We're working through this mechanism one step at a time. Yep, we're going to deprotonate water and we'll protonate our amine to activate it as a leaving group. Yep, exactly right. Perfect. So let's just annotate those next few steps. So we protonate our amine. We deprotonate our alcohol. We've now activated our amine as a leaving group. So we can kick out our amine, and that in turn gives us the protonated ketone. Which can just be deprotonated with water or another reasonably basic solvent component. And that in turn gives us our neutral isolable product. Does this mechanism and does this general mechanism for the Stork enamine reaction make sense? Any questions on this mechanism? Okay, so let's keep going then. And let's talk about an application of the Michael reaction and Aldol reaction into a cascade reaction known as the Robinson annulation. This is a two-step reaction that combines a Michael reaction with an intramolecular Aldol reaction. This is a great way to prepare substituted cyclohexenones. And the process works best if your nucleophilic enolate is less basic than the enone-derived enolate. So in this mechanism, as always, we're going to start with a malonate or a beta ketoester. In the case of the Robinson annulation, this starts from a beta ketoester because it's easy to generate the enolate. From here, we're going to deprotonate our acidic alpha position to generate our enolate. This enolate, being a relatively strong nucleophile, can react with electrophiles such as methyl vinyl ketone to generate our conjugate addition product. Okay, now if we think about this substrate for a moment, we'll notice that the enolate that we form after conjugate addition is not the best enolate for a productive reaction. So as we notice, if we tried to form this bond, this would be a 4-membered ring, not favorable. But if we used our other alpha position, it would be a 6-membered ring, which is favored. So with that analysis in mind, thinking about the next step, which is an intramolecular aldol reaction, what we're going to do is we're going to see a proton transfer step. First, we're going to protonate our enolate. And this is all an equilibrium process, because remember, the Michael reaction and Aldol condensations are reversible up until their final, very important key step. Okay, so we've protonated our enolate, and I'm going to redraw this molecule now in a way that's a little bit more indicative of what's going on here. Okay, so now we've redrawn this substrate, and we see that we can now deprotonate our alpha position. From here now, our enolate can attack our electrophilic carbonyl carbon, and that in turn gives us a 6-membered ring. From here now, we can protonate this alkoxide ion. That in turn gives us our beta hydroxy ketone. And then from here, deprotonation followed by elimination of hydroxide yields our desired enone product. There should be a methyl group here. There we go. Does this general mechanism for the aldol for the Claisen reaction, which includes a Michael addition followed by an aldol reaction, make sense to everyone? Does this mechanism for the Claisen condensation make sense? Any questions on this mechanism that I can address? As you notice, it just combines two reactions that we've seen before. Any questions before we try to apply what we've learned to an example? So let's try to apply what we've learned now. But before we do that, let's just recap the key steps for the Robinson annulation. First, we deprotonate and make our enolate. Then our enolate adds 1,4 into our enone, and we get a 1,5 diketone. From here, we have an intramolecular Robinson annulation. Although we have two possible positions, alpha 1 and alpha 2, reaction at alpha 1 would give a 4-membered ring, which is not favored under the equilibrating aldol conditions. Instead, we deprotonate at our other alpha position. One moment. Instead, we deprotonate at our other alpha position. And from here, this enolate can attack our electrophilic carbonyl carbon to form a 6-membered ring. From here, protonation of our alkoxide ion, followed by elimination of hydroxide, generates our desired enone product. Does this mechanism make sense to everyone? And do the key steps from the Robinson annulation mechanism make sense? Okay, so let's try to apply what we've learned to the following example, and let's try to predict the product from the following reaction, and then draw a mechanism for the following reaction. So as we work through this next example, I'd like students to share their proposed responses as either a photo of their written work in the chat. You can share your proposed mechanistic steps verbally, or you can annotate your proposed mechanism on the class whiteboard. So as we work through this example, let's take about 4 to 5 minutes, and then we'll discuss throughout this problem solving period. So we have this beta diketone, or this 1,3 diketone, and we're treating it with sodium hydroxide followed by an electrophilic enone. So what will happen in this reaction? What's the first thing that's going to happen? Does anyone have a thought or a perspective? What will happen if we have this acidic 1,3 diketone and we're reacting it with a base? What's the first step that's going to happen? How are we going to generate our nucleophile? Does anyone have a proposal for this reaction? Would anyone like to share their proposed mechanism for this problem? So for the first step, we have students noting that hydroxide is sufficiently basic to pull off our alpha proton and generate our enolate. Yep. So this 1,3-diketone is relatively acidic. So hydroxide is basic enough to deprotonate our alpha position and generate our enolate. Now, once we've formed our enolate, what's going to happen next? So we now have our nucleophilic enolate. Are there any electrophiles that can react with our enolate? Yep, we're going to attack the beta carbon of our enone. And we're going to form an enolate. Sure. So right now we have a textbook conjugate addition reaction. So we form the following product. So what will happen next? Would anyone like to detail the next step for this reaction? So initially this intramolecular reaction wouldn't work. It would give a four-membered ring, which is not particularly favorable. However, we can set up this substrate for a productive reaction. So how do we set up this compound? How do we make an enolate that can actually react via an aldol reaction? Proton transfer, yep. So first we can protonate our enolate. And then from here, we can then deprotonate the other alpha position. That in turn gives us the following new enolate product. So now what happens? So now that we have our nucleophilic enolate all set up, what can we do with this? The enolate will attack one of these ketone carbonyl carbons. It actually doesn't matter which one because they're identical. So that forms our key 5,6 ring system. And now from here, what happens next? So we get our beta hydroxyketone. Sure. And what's our key step that drives this reaction to be product favored? So if we treat this beta hydroxyketone with hydrochloric acid, what do we see? What happens next? How do we drive the equilibrium for the Aldol reaction to completion? How do we drive this equilibrium to favor the products? So the Aldol reaction is typically reversible up until a key finishing step. So we have to eliminate this alcohol, and the best way to do that under acidic high temperature conditions is via protonation of the alcohol, followed by elimination of water. Exactly right. So with that, we get our isolated 5,6 enone. The Robinson annulation has been used to prepare a range of very useful enone substrates that have been used in a range of organic syntheses. Does this mechanism make sense to everyone? Any questions on the Robinson annulation? Any questions before we close out today's lecture block? We finished chapter 23. Any questions on chapter 23 I can address before we archive today's recording? If there aren't any questions, then we'll archive today's recording.